The Constants of Nature, a journey into the foundations of reality. Beneath the beauty and complexity of the cosmos lies a profound enigma, the constants of nature. These numbers, woven into the fabric of reality, dictate the behavior of everything from subatomic particles to galaxy clusters. Yet, their origins remain one of the deepest mysteries of physics. In the 1940s, physicist Richard Feynman grappled with one such mystery. His groundbreaking work in quantum electrodynamics, QED, explained how electrons interact with light, earning him a Nobel Prize. But one number haunted him, the fine structure constant. All good theoretical physicists put this number up on their wall and worry about it, Feynman remarked. Immediately you would like to know where this number comes from. Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. The fine structure constant, approximately equal to 1/137, measures the strength of electromagnetic interactions. Without it, QED, and much of modern physics, would collapse. Yet, its precise value cannot be derived from theory, it must be measured experimentally. Decades later, physicists still ponder the same question that vexed Feynman: why 1 of 137? The fine structure constant is just one of many constants that underpin our understanding of the universe. These numbers dictate the laws of physics, from the speed of light to Planck's constant, which governs the quantum realm. Others, such as quark mixing angles and Yukawa couplings, reside in the intricate mathematics of advanced particle physics. Without these constants, our theories would be meaningless, unable to describe the interactions that shape reality. Constants like these are more than mathematical curiosities. They hold the keys to understanding the universe's very existence. From the forces that bind particles to the behavior of gravity, these values determine not only how the universe functions but also why it appears as it does. To appreciate the significance of these constants, let us take a journey inward, peeling back the layers of our existence. Begin with a human being, a complex assembly of organs and systems working in harmony. Delve deeper, and you find that these organs are made of cells, each a microscopic marvel of interacting proteins, lipids, and nucleic acids. Zoom further in, and molecules dissolve into atoms, the building blocks of matter. Atoms, in turn, reveal an even simpler structure. Protons and neutrons, nestled in the atomic nucleus, are orbited by electrons. Yet even here, the simplicity is deceptive. Protons and neutrons are composed of smaller particles, quarks, held together by the strong nuclear force. At this fundamental level, we find a universe built from a handful of components, quarks and electrons, bound together by the fundamental forces. These forces, strong, electromagnetic, weak, and gravitational, are the glue of existence. The strong force binds quarks into protons and neutrons and holds atomic nuclei together. Electromagnetism tethers electrons to nuclei, forming atoms. Gravity, though weak on the atomic scale, gathers matter into planets and stars. The weak force governs radioactive decay and nuclear reactions, playing a crucial role in the evolution of stars. Each force depends on constants of nature. The strength of the strong force, the gravitational constant, and the fine structure constant all determine how these forces interact. Without them, the universe as we know it could not exist. But why do these constants have their particular values? Could they have been different? This question leads to one of the most profound puzzles in physics, the apparent fine-tuning of the universe. The constants of nature seem precisely calibrated to allow for the existence of life. Change them slightly, and the universe could become a barren wasteland. For example, if the strong force were slightly weaker, atomic nuclei would not hold together, and no elements beyond hydrogen would form. If the electromagnetic force were stronger, stars would burn out too quickly to support life. Such fine-tuning raises tantalizing questions. Was the universe designed to be this way? Or do we inhabit one of many universes, each with its own set of constants, with ours merely one where life is possible? These are questions that science has yet to answer, but they force us to confront the delicate balance that makes existence possible. To understand the origins of these constants, we must journey back to the beginning of time, the Big Bang. In the universe's earliest moments, temperatures and densities were unimaginably high, and the laws of physics as we know them began to take shape. As the universe expanded and cooled, particles and forces emerged, and the constants of nature crystallized into their present values. But why these values? The standard model of particle physics, though incredibly successful, offers no explanation for the origins of these constants. They are inputs to the theory, not outputs. Some physicists speculate that a deeper theory, perhaps string theory or a multiverse framework, might explain them. Others believe that understanding the constants will require insights that transcend current scientific paradigms. Science thrives on what-if questions. What if the fine structure constant were slightly different? What if the speed of light were faster or slower? Exploring these hypothetical scenarios reveals how profoundly the constants of nature shape our universe. In many cases, even minor changes would render the universe inhospitable to life. This sensitivity underscores the importance of these numbers and deepens the mystery of their origins. The constants of nature sit at the intersection of physics and philosophy. They are both deeply practical, allowing us to calculate and predict the behavior of the universe, and profoundly mysterious, hinting at questions about existence itself. Why does the universe have these particular constants? Are they fixed, or could they vary across time and space? And, perhaps most intriguingly, do they offer clues about why the universe exists at all? Feynman's wonder at the fine structure constant encapsulates the awe and curiosity that drive scientific inquiry. These constants remind us that even in an age of technological and theoretical advances, some mysteries remain as tantalizing as ever. They challenge us to look beyond the equations, to seek the deeper truths that govern reality, and to continue the eternal quest to understand not just how we are here, but why. Are you special? The anthropocentric puzzle in a vast universe. What if the universe were different? What if the stars burned dimmer, gravity pulled weaker, or the forces governing atomic interactions were slightly altered? Would the galaxies still spin? Would planets like Earth form? Would we, sentient beings capable of pondering these questions, exist at all? The answers to these questions lie at the intersection of physics, cosmology, and philosophy, weaving a narrative about our place in the cosmos that is as humbling as it is profound. From the vantage point of Earth, it is tempting to believe that the universe was crafted with us in mind. Early civilizations certainly thought so. To the Babylonians, our world was a flat, circular disk surrounded by the chaos of infinite waters. The Greeks and Romans saw the stars as a celestial stage for gods and monsters, while ancient Chinese cosmology imagined the heavens as concentric shells revolving around Earth. Science, however, has steadily dismantled this comforting illusion. In 1543, Nicholas Copernicus shattered the geocentric worldview, placing the Sun at the center of our planetary system. This dethroning of Earth continued into the 20th century as Edwin Hubble's telescopes revealed that our Sun is but one of billions of stars in the Milky Way, which itself is just one of potentially trillions of galaxies in the observable universe. Today, the cosmos appears boundless, vast, and largely indifferent to our existence. This growing sense of insignificance is formalized in the Copernican principle, a cornerstone of modern cosmology. It asserts that Earth occupies no special place in the universe. The laws of physics are uniform across space and time. From any vantage point, the universe looks essentially the same. Humanity, in this view, is not central but peripheral, a mere bystander in a vast cosmic drama. While the Copernican principle encourages humility, it does not fully explain why we observe the universe as we do. In the 1960s, Princeton astrophysicist Robert Dicke introduced a temporal dimension to this question. Dicke argued that intelligent observers like us could only exist at specific epochs in the universe's history, a conclusion rooted in the physics of stellar evolution. In the universe's infancy, heavy elements such as carbon and oxygen did not exist. These elements, essential for life, were forged deep within the cores of the first stars and scattered across space when those stars died. It took billions of years for subsequent generations of stars to enrich the cosmos with the building blocks of complexity. Conversely, in the distant future, the universe will grow increasingly inhospitable as stars like our Sun exhaust their fuel and fade into white dwarfs, leaving only dim red dwarfs to light the cosmos. Life as we know it can only emerge during a relatively narrow window, a golden age of habitability, which we currently inhabit. In 1973, Australian physicist Brandon Carter expanded on this idea at a conference marking Copernicus's 500th birthday. Carter proposed the anthropic principle, a counterpoint to the Copernican principle. While our location in space may be unremarkable, he argued, our existence imposes constraints on the conditions we observe in the universe. For intelligent life to arise, the cosmos must meet certain prerequisites, and these prerequisites are anything but ordinary. At the heart of the anthropic principle lies a delicate balance. The universe's fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, determine everything from the behavior of stars to the chemistry of life. These forces are governed by constants of nature, unchanging numbers that dictate their strength and interactions. Slight variations in these constants would lead to a radically different universe. For example, if gravity were slightly stronger, stars would burn through their fuel too quickly, leaving insufficient time for complex life to evolve. If it were weaker, stars might never ignite, and planets like Earth would not form. Similarly, if the electromagnetic force were altered, atoms would not bind together properly, rendering chemistry and life impossible. The strong nuclear force, responsible for binding protons and neutrons in atomic nuclei, must also be finely tuned. A slight increase in its strength would prevent the formation of hydrogen, the most abundant element in the universe, while a slight decrease would destabilize all nuclei. This fine-tuning extends to the elements themselves. The iron in Earth's core, the silicon in its crust, the oxygen in water, and the carbon in living organisms all owe their existence to the precise conditions within stars. Gravity compresses stellar cores to immense densities and temperatures, enabling nuclear fusion. Through fusion, lighter elements like hydrogen and helium are transformed into heavier elements. Over billions of years, the cycle of stellar birth, death, and rebirth has enriched the universe, creating the raw materials for planets and life. The anthropic principle raises profound questions. Are the constants of nature the way they are by design, or are they the product of chance? Some physicists suggest that our universe is just one of many in a multiverse, each with its own set of physical laws. In this scenario, we inhabit a universe where the conditions happen to be right for life because, by definition, only such a universe could produce observers to ponder its nature. Others see fine-tuning as evidence of a deeper, underlying principle or even a designer. The anthropic principle does not resolve these debates but instead highlights the extraordinary set of circumstances that make life possible. It challenges us to think about the universe not just as a backdrop for existence but as a participant in the story of life. The questions do not end here. What if gravity were slightly stronger, electromagnetism slightly weaker, or the laws of physics entirely different? Would stars still shine, or would the universe be a dark, lifeless expanse? Exploring these what-if scenarios helps physicists understand the robustness of the universe's design and the constraints that govern its evolution. As we ponder these questions, one thing becomes clear. While we may not occupy the center of the universe, our existence is deeply tied to its fundamental properties. The forces and constants that shape the cosmos also shape us, linking the vast and the minute in a delicate, interdependent web. The magic numbers, constants of nature and the universe's blueprint. Would stars still ignite? Would atoms form? Would life, as we know it, even exist? These questions probe the very heart of physics, revealing how the universe's magic numbers shape everything we observe and experience. At the dawn of the 20th century, physics faced a conundrum. Scientists could not explain why objects glowed the way they did when heated, shifting in color from red to white. Max Planck, one of the era's most brilliant minds, sought a solution. He experimented with classical ideas, only to find them inadequate. Desperate, Planck introduced a radical concept: energy is quantized, emitted and absorbed in discrete packets he called quanta. Planck's innovation was born not from clarity but from necessity. What he considered a mathematical trick turned out to be the foundation of quantum mechanics, a paradigm shift that redefined physics. Embedded within his equations was a number, Planck's constant, that became central to understanding the quantum realm. This constant explained phenomena as varied as the glow of hot objects, atomic structures, and the interaction of light and matter. Today, Planck's constant is a cornerstone of quantum physics, a reminder that even the most desperate ideas can illuminate new paths. Physics is written in the language of mathematics, a precise tool for describing and predicting the universe's behavior. Newton's laws of motion tell us how objects move, while Maxwell's equations describe the interplay of electricity and magnetism. Yet, these equations require something more: the values of the constants of nature. Without these constants, the equations are mere abstractions, unable to connect theory with reality. For example, Newton's law of gravitation depends on the gravitational constant, which measures the strength of gravity. Maxwell's equations rely on the permittivity and permeability of free space to define the propagation of electromagnetic waves. These constants are not derived from theory, they are measured, extracted from the natural world through meticulous experiments. In 1798, Henry Cavendish conducted one of the most delicate experiments in scientific history. Using a torsion balance housed in a wooden box to shield it from disturbances, Cavendish measured the gravitational attraction between lead spheres. His work revealed the density of the Earth and provided a means to calculate the gravitational constant. Cavendish's weighing of the world was an extraordinary achievement, with his results remaining unmatched in precision for a century. Today, the quest for precision continues. Constants like the speed of light and Planck's constant are known to astonishing accuracy, often to many decimal places. These values anchor the equations of physics, making them indispensable tools for exploring the universe. Beyond gravity and light, other constants define the universe's behavior. The strength of the Higgs field determines the masses of fundamental particles. Quark mixing angles govern how quarks transform into one another, influencing the behavior of matter at the subatomic level. These constants are cataloged in physics textbooks, serving as the foundation for scientific inquiry. Dimensionless constants, which lack units, are particularly significant. For instance, the fine structure constant, approximately equal to 1/137, measures the strength of electromagnetic interactions. Another example is the ratio of the proton's mass to the electron's mass, roughly 1836. These numbers are universal, unaffected by the units we choose to describe them. Yet their origins remain a mystery. Why 1/137? Why 1836? What if these numbers had been different? To understand the importance of these constants, physicists simulate hypothetical universes with altered values. What if gravity were 1,000 times stronger? Planets would orbit their stars more rapidly, stars would burn through their fuel faster, and the cosmos would evolve at a breakneck pace. What if electromagnetism were weaker? Atoms might fail to form stable bonds, rendering chemistry and life impossible. Such thought experiments reveal the fragility of our universe's design. Small changes to the constants of nature could render the cosmos unrecognizable. The fine-tuning evident in these constants suggests a profound connection between the laws of physics and the emergence of complexity. To truly grasp the impact of the constants, we must journey back to the universe's beginning. In the moments after the Big Bang, temperatures and densities were extreme. fundamental forces began to emerge, their strengths encoded in the constants we observe today. These forces shaped the cosmos's evolution, guiding the formation of atoms, molecules, stars, and galaxies. Gravity, electromagnetism, and the nuclear forces worked in harmony to create the elements necessary for life. Stars fused hydrogen and helium into heavier elements, scattering them across space when they exploded as supernovae. These elements coalesced into planets, setting the stage for the emergence of life. Altering the constants would disrupt this delicate balance, potentially preventing the universe from ever reaching such complexity. The apparent fine-tuning of the constants raises profound questions. Why do they have the values they do? Some physicists suggest that our universe is one of many in a vast multiverse, each with its own set of constants. In this view, we exist in a universe where the conditions happen to allow for life, simply because only such a universe could produce observers to ponder its nature. Others propose that deeper principles, as yet undiscovered, dictate the values of these constants. String theory and other frameworks offer tantalizing hints, but the ultimate answers remain elusive. The fine-tuning of the constants invites both scientific and philosophical reflection, challenging us to explore the intersection of necessity, chance, and design. The constants of nature are the universe's magic numbers, governing everything from the motion of planets to the behavior of subatomic particles. They are the scaffolding on which the cosmos is built, their precise values enabling the emergence of complexity in life. Changing the rules of nature, a journey through hypothetical universes. As we peer into this multiverse of possibilities, we begin to grasp how uniquely fine-tuned our universe truly is, and why life, as we know it, might be an exceedingly rare phenomenon. Modern astronomy has achieved remarkable success in explaining the universe by adhering to the rules of physics. Around the globe, scientists use supercomputers to construct synthetic universes, translating the equations of cosmology and astrophysics into intricate computational models. These simulated universes, spanning billions of light years and billions of years, provide a window into cosmic evolution. Projects like the illustrious TNG trace the interplay of matter and radiation within expanding, synthetic universes. These virtual realities reveal the dance between cosmic expansion, which pulls matter apart, and gravity, which draws it together. In these simulations, matter clumps into proto-galaxies, gas flows into stars, and the life cycles of stars play out. Some stars end their lives in brilliant supernovae, scattering heavy elements into space, while others quietly fade into white dwarfs. The simulations track how these elements, the building blocks of complexity, are formed and dispersed. Inspection of these synthetic universes reveals familiar structures, galaxies, star clusters, and clouds of gas. Some are pristine remnants of the Big Bang, while others are enriched with heavier elements forged in stellar cores. The striking resemblance between these synthetic universes and our own confirms that the laws of physics govern the cosmos's evolution, from the largest galaxy clusters to the smallest atomic interactions. If we can construct synthetic universes based on our own physics, why not imagine universes governed by different rules? The process seems deceptively simple: tweak the constants of nature, adjust the computer code, and observe the results. But is it truly that straightforward? We are the result of a complex web of interactions spanning billions of years. To determine whether life could arise in other universes, we must unravel this web, cutting its threads and forging new connections. Simplified models provide insights, but to capture the full complexity of alternate realities, scientists rely on supercomputers to simulate hypothetical universes. The results are sobering: most possible universes are lifeless and sterile. Calculations reveal a vast ocean of dark, barren universes. In many, there is no structure, no galaxies, stars, or planets. In others, complexity fails to arise. There is no periodic table of elements to support chemistry. Amid this bleak landscape, islands of complexity and potential habitability are vanishingly rare. In our universe, the masses of the fundamental up and down quarks are finely balanced. This balance ensures that the proton is lighter than the neutron, causing neutrons to decay into protons shortly after the Big Bang. This decay filled the cosmos with protons, forming the hydrogen atoms that fuel stars and serve as the foundation for heavier elements. If the down quark were lighter, neutrons would be less massive than protons. The Big Bang would have produced a universe awash with inert neutrons. Stars composed of neutrons might form, but without the nuclear reactions that fuse elements, there would be no periodic table, no complex chemistry, and no life. Conversely, a heavier down quark could destabilize protons, erasing hydrogen and snuffing out the possibility of star formation. Electrons orbit atomic nuclei, enabling the formation of molecules. Their mass, relative to the nuclear force, dictates the stability of these orbits. In our universe, the nuclear force is thousands of times stronger than the electromagnetic force, ensuring stable atoms and diverse chemistry. If electrons were more massive, their high-speed orbits would cause nuclei to wobble. This instability could prevent atoms from bonding, leaving a universe populated only by individual atoms, a gas with no molecules, no solids, and no life. Chemistry, the engine of complexity, hinges on this delicate balance. Gravity plays a pivotal role in shaping the universe. It draws matter together to form galaxies, stars, and planets. But its strength must be just right. If gravity were weaker, the expanding universe would remain a diffuse soup of hydrogen, never coalescing into stars or galaxies. If gravity were stronger, matter would collapse into black holes before stars could ignite. Even within this narrow range, gravity dictates the lifetimes of stars. Too weak, and stars fail to sustain nuclear reactions, remaining as inert balls of gas. Too strong, and stars burn through their fuel too quickly, leaving no time for the evolution of life. In our universe, dark energy drives the accelerating expansion of space. During the universe's early epochs, matter dominated, allowing gravity to draw material into stars and galaxies. Approximately 5 billion years ago, dark energy overtook matter as the dominant force, accelerating the universe's expansion. If dark energy were stronger, this acceleration would have begun earlier, preventing matter from collapsing into stars. Hydrogen atoms would drift alone in cold, empty space. Conversely, a universe without dark energy might eventually collapse under gravity's pull, snuffing out the possibility of long-term complexity. The balance between dark energy and matter determines the universe's fate and its potential for life. Beyond gravity, dark energy, and particle masses, other constants influence habitability. The speed of light, the scale of quantum mechanics, and the stability of dark matter all play roles in shaping the cosmos. For some constants, small changes yield negligible effects. For others, even a slight adjustment would render the universe unrecognizable and uninhabitable. Among the multiverse's countless possibilities, our universe stands out as a rare exception. It is an island of complexity in a sea of sterility, its constants perfectly balanced to support life. This realization answers one question: how are we here? We exist because of an almost impossibly precise interplay of physical laws, honed over 13.8 billion years. But this answer raises a deeper, more profound question: why? Why does our universe have the rules it does? Are these constants the result of chance, necessity, or something beyond our comprehension? As we continue to explore the multiverse and the fundamental laws of nature, we inch closer to understanding not only how we exist but why the universe is the way it is. Why are we here? Exploring the enigma of existence. The constants of nature have long fascinated physicists, their seemingly arbitrary values shaping the cosmos in profound ways. From the speed of light to the gravitational constant, these numbers dictate the behavior of the universe at every scale. For some, their precise values seem to demand explanation, hinting at a deeper truth hidden within the fabric of reality. Take, for example, the fine structure constant. This dimensionless number, approximately equal to 1/137, measures the strength of electromagnetic interactions. Sir Arthur Eddington, the first to experimentally confirm Einstein's general theory of relativity, was captivated by this number. He speculated that it might be exactly 1/137, even connecting it to the total number of protons in the observable universe. But as experimental measurements became more precise, Eddington's hypothesis fell apart. The fine structure constant is not tied to any simple integer, and its true nature remains a mystery. As science advances, the web of constants needed to describe the universe grows smaller. Before James Clerk Maxwell, electricity and magnetism were described by separate constants. Maxwell's equations unified these forces, introducing a single constant, the speed of light. Such unifications hint at the possibility of an ultimate theory, a theory of everything that might dispense with constants altogether, reducing physics to pure mathematics. But would such a theory truly answer the question of why we are here? Or would it simply shift the question to a higher level? Even if the laws of physics could be expressed as mathematical relationships without constants, we would still be left asking why these relationships permit the existence of a universe capable of hosting life. This brings us to the concept of fine-tuning. The constants of nature are not just arbitrary numbers, they appear delicately balanced to allow for complexity, structure, and life. A slight alteration in the gravitational constant, for instance, could prevent stars from forming, while a change in the fine structure constant might disrupt the chemistry necessary for life. Such precision has led some to propose that the universe was designed with purpose, perhaps by a divine being or fine-tuner. The fine-tuning argument aligns with many religious worldviews, suggesting that the universe's life-permitting properties are evidence of intentional creation. Yet, alternative explanations challenge this perspective, offering visions of existence that are no less profound. One such alternative is the simulation hypothesis, championed by Oxford philosopher Nick Bostrom. According to this idea, our universe could be a sophisticated simulation run by a higher intelligence. As computers become more powerful, humans may one day simulate entire universes, complete with conscious beings who perceive their reality as genuine. If such simulations are possible, it follows that our own universe might be a simulation created by an advanced civilization. The laws of physics would then be nothing more than computer code, optimized to produce an interesting universe. In this framework, we find ourselves in a universe with life and complexity because a simulated cosmos devoid of these features would be unworthy of computational resources. While the simulation hypothesis is philosophically intriguing, it poses challenges for empirical science. How can we test whether we are living in a simulation? If our reality is governed by computer code, then any attempt to investigate the base reality might be inherently limited. And even if we accept the hypothesis, it raises further questions. Is the universe simulating us also a simulation? Are there turtles all the way up? Another explanation for fine-tuning lies in the concept of the multiverse. Rather than being unique, our universe could be one of countless others, each with its own set of physical laws. In this scenario, the constants of nature vary across universes, their values determined by a random process. Most universes would be sterile, lacking the conditions necessary for life. Ours, however, is one of the rare exceptions, its constants coincidentally aligned to permit complexity. The multiverse hypothesis shifts the question from why are the constants fine-tuned to why do we observe this universe? The answer is anthropic. We exist because we inhabit a universe that allows for observers. If the multiverse is real, then our existence is not special but inevitable within the subset of universes that support life. Despite its appeal, the multiverse hypothesis faces significant criticism. Some argue that it is wasteful, positing an infinite array of lifeless universes to explain one that harbors life. Others contend that it is unscientific, as the existence of other universes may be fundamentally untestable. Without observational evidence or predictive power, the multiverse remains more a philosophical concept than a scientific theory. Whether through divine intervention, computational simulation, or the multiverse, the question of why we are here continues to elude definitive answers. Each explanation offers insights but also raises further questions. Why would a creator fine-tune the universe? Why would a simulation prioritize complexity? Why does the multiverse generate universes at all? These questions remind us that our understanding of existence is still in its infancy. As we probe deeper into the cosmos and refine our theories, we may uncover new principles that shed light on the mystery of our origins. For now, the search for answers is as much about the journey as the destination, inspiring us to explore, imagine, and question. Why are we here? This question transcends science, touching on philosophy, theology, and the human condition. It challenges us to consider our place in the universe, not just as passive observers but as active participants in the unfolding story of existence. As we grapple with this enigma, we are reminded of the vastness of the cosmos and the improbability of life. Whether we are the product of divine design, computational artistry, or cosmic chance, our existence is a testament to the complexity and wonder of the universe. And in seeking to understand it, we honor the very curiosity that makes us human. Begin and where does it end? Could the very existence of life, stars, and galaxies hinge on a delicate cosmic imbalance? To understand why the universe as we know it exists, we must first unravel the principles of balance, principles that govern not just our world but the entire cosmos. The foundation of reality, as we understand it, relies on a principle as ancient as time itself: balance. Energy can neither be created nor destroyed, it simply changes form. For every action, there is a reaction. What goes in must come out. This principle, rooted in the conservation laws of physics, dictates the behavior of everything from atoms to galaxies. In the 17th century, Italian physician Santorio sought to explore balance within the human body. Driven by curiosity, he embarked on a decades-long experiment. For 30 years, he meticulously weighed every liquid and solid he consumed and every excretion he produced. He weighed himself before and after physical exertion, keeping a daily record of matter in, matter out. Yet, Santorio encountered a puzzling mystery: the mass of his excretions never matched the mass of his food and drink. It was as though the human body, like a campfire, consumed matter and left behind something far less substantial than what it had started with. Santorio's instincts were correct. Matter does not simply vanish. By the 18th century, natural philosophers proved that the total mass before and after a chemical reaction is conserved. This revelation illuminated the workings of metabolism and combustion. Whether breaking down food into fats, proteins, and sugars or burning wood into ash, carbon dioxide, and water, every chemical equation balanced out. Atoms merely rearranged themselves, ensuring that the total count remained constant. Yet, even as this principle held true for most reactions, the universe itself began to challenge its own rules. The sun, the very source of daylight, provided a paradoxical clue that balance might be more complex than it first appeared. In the 20th century, humanity unlocked the nuclear secrets of the atom. Deep within the sun's core, hydrogen nuclei fused to form helium, releasing immense energy in the process. However, the mass of the resulting helium is less than the combined mass of the original hydrogen. The reaction seemed unbalanced. Where had the missing mass gone? A young Swiss patent clerk, Albert Einstein, provided the answer with his revolutionary equation. Mass, Einstein revealed, is not an isolated property but a form of energy. The missing mass from the sun's reactions is converted into photons, the sunlight that illuminates our days. Balance, though subtle and transformed, is ultimately restored. If the universe tends toward balance, then why does it seem so profoundly unbalanced? Nearly everything we see, touch, and experience is made of matter. From the atoms in our bodies to the stars in distant galaxies, the universe is overwhelmingly composed of matter. Yet, for every particle of matter, there exists an almost identical counterpart, antimatter. Antimatter particles mirror their matter twins in mass but carry opposite charges. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter meets antimatter, the two annihilate each other, releasing pure energy. If the early universe began in perfect balance, with equal parts matter and antimatter, then why is there such an overwhelming abundance of matter today? Where has all the antimatter gone? The imbalance between matter and antimatter is one of the most profound mysteries of modern physics. Without this asymmetry, the universe would be a vastly different place. No stars would shine. No planets would form. No life would exist. The cosmos would be a void of light and structure, filled only with radiation from matter-antimatter annihilations. Yet, the observable universe defies this fate. Somehow, in the earliest moments after the Big Bang, a subtle asymmetry emerged. For every billion particles of antimatter, there was 1,000,000,001 particles of matter. The excess matter survived annihilation, seeding the formation of galaxies, stars, and planets. This imbalance, infinitesimally small yet cosmically significant, is the reason we are here. How did this imbalance arise? Scientists have proposed various mechanisms, including processes known as baryogenesis. These theories suggest that tiny differences in the behavior of matter and antimatter, governed by the weak nuclear force, could have tipped the scales. Experiments, such as those conducted at particle accelerators like CERN, continue to probe the fundamental properties of matter and antimatter, searching for clues to this cosmic puzzle. As we gaze into the night sky, the vastness of the universe confronts us with its apparent contradictions. A cosmos that began in perfect symmetry now teems with imbalance, its laws both balanced and unbalanced in ways that sustain complexity and life. This paradox lies at the heart of existence. Why does the universe appear so perfectly balanced at its inception, only to evolve into a realm where imbalance gives rise to structure, light, and life itself? The journey of antimatter, from theory to discovery. The story of antimatter is one of the most fascinating and fundamental chapters in the history of physics, intertwining theoretical breakthroughs with experimental triumphs. The most famous equation in physics encapsulates the relationship between mass and energy. In this equation, represents the ultimate speed limit of the universe, the speed of light traveling unimpeded through the vacuum of space. Simple in appearance, this equation underpins Einstein's theory of relativity, which reshaped humanity's understanding of space, time, and energy in the early 20th century. This era marked a revolution in physics, where concepts once unimaginable began to reveal the universe's secrets. Among the brilliant minds of this transformative period was Paul Dirac, a theoretical physicist from Bristol. Dirac's contributions would not only extend Einstein's insights but also uncover an entirely new realm of existence. Born in 1902, Paul Dirac's journey began with engineering studies before transitioning to mathematics, earning his PhD from Cambridge in 1926. Known for his precision in thought and speech, Dirac's retorts during lectures were as incisive as his scientific insights. To fellow physicist Niels Bohr, he once advised, "Never start a sentence without knowing the end of it." By the mid-1920s, quantum mechanics was revolutionizing our understanding of the subatomic world. Electrons and protons, the only known particles at the time, could be described both as particles and waves. In 1926, Erwin Schrödinger published his foundational equation describing quantum systems. Yet, as Dirac examined this new framework, he realized it was incomplete. Schrödinger's equation did not account for the effects of Einstein's relativity. Dirac set out to unify quantum mechanics and relativity. His work culminated in the Dirac equation, a more comprehensive mathematical description of particle behavior. Years later, when asked about his groundbreaking discovery, Dirac's response was characteristically succinct: "I found it beautiful." Dirac's equation revealed a startling implication. While electrons had been understood to exist only with positive energy, the mathematics suggested they could also possess negative energy. This posed a problem. If negative energy states existed, electrons should continuously spiral into them, emitting infinite amounts of light in the process. Clearly, this was not the case in the observable universe. To resolve this paradox, Dirac proposed the existence of a sea of negative energy states, later known as the Dirac sea. In this model, all negative energy states were already filled, preventing electrons from falling into them. However, if an electron were given enough energy, it could leap out of the Dirac sea, leaving behind a hole. This hole would behave like a particle with the same mass as an electron but with opposite charge, an anti-electron. In 1931, Dirac proposed the existence of antimatter. Initially, he speculated that the anti-electron might be the proton, which was already known to have a positive charge. However, the proton's much greater mass ruled out this possibility. Dirac's anti-electron, later called the positron, remained a theoretical prediction, awaiting experimental confirmation. While Dirac's equations laid the groundwork, it was Carl Anderson who provided the proof. In 1931, Anderson began studying cosmic rays, particles streaming across the universe, using a cloud chamber. This device, filled with water vapor, allowed charged particles to leave visible trails as they passed through. Anderson observed a trail that mirrored those of electrons but curved in the opposite direction under a magnetic field. This indicated a particle with the same mass as an electron but with a positive charge. In 1932, Anderson published his findings, naming the particle the positron. Dirac's theoretical antimatter had become a reality. The discovery of the positron marked the beginning of an era. While positrons could occasionally be found in cosmic rays, other antiparticles were far rarer. Physicists turned to particle accelerators to create antimatter artificially. By colliding particles at high speeds, they converted kinetic energy into mass, producing showers of particles and their corresponding antiparticles. In 1955, scientists at the Bevatron Accelerator at Lawrence Berkeley National Laboratory created the antiproton. A year later, they discovered the antineutron. These discoveries expanded the antimatter catalog and opened new avenues for research. However, creating an entire antiatom remained a daunting challenge. In 1995, nearly 4 decades after the discovery of the antiproton, researchers at CERN achieved a monumental breakthrough. Using the low-energy antiproton ring, they combined antiprotons with positrons to create 9 antihydrogen atoms. This marked the first time an antiatom had been synthesized in the laboratory. Further advancements came in the following decades. By 2010, CERN scientists had developed techniques to trap antihydrogen atoms for extended periods. These experiments allowed researchers to study the properties of antimatter in unprecedented detail. Their findings confirmed that antihydrogen behaved almost identically to regular hydrogen, including its interactions with light. Antimatter holds profound implications for our understanding of the universe. Dirac's work not only expanded the boundaries of quantum mechanics but also raised new questions about the nature of reality. If antimatter mirrors matter so perfectly, why does the observable universe contain so little of it? The apparent asymmetry between matter and antimatter remains one of the greatest mysteries in modern physics. Additionally, antimatter offers tantalizing possibilities for technology. In theory, matter-antimatter annihilation could provide an incredibly efficient energy source. However, the practical challenges of producing and storing antimatter on a large scale remain formidable. Paul Dirac's pursuit of beauty in mathematics led to one of the most significant discoveries in physics. From the theoretical prediction of the positron to the creation of antihydrogen, the story of antimatter exemplifies the interplay between theory and experiment. Nearly a century after Dirac's groundbreaking work, his insights continue to inspire scientists, inviting us to explore the boundaries of the known universe and the mysteries that lie beyond. Where is all the antimatter? Imagine a world where humanity harnesses the boundless power of antimatter. What do you see? Do you envision massive interstellar starships racing through the cosmos, expanding our reach to habitable worlds light years away? Extraterrestrial colonies braving harsh or Eden-like landscapes, staring out at twin suns setting on alien horizons? Or perhaps a far darker vision, desolation, the aftermath of an untamed technology, a power station explosion dwarfing Chernobyl and Fukushima, humanity's frailty magnified by mutual annihilation. These scenarios, both awe-inspiring and terrifying, stem from the immense potential of matter-antimatter reactions, the most fuel-efficient process known in physics. According to Einstein's famous equation, the annihilation of matter and antimatter results in the total conversion of mass into energy. Gram for gram, matter-antimatter annihilation releases energy over 100 times greater than nuclear reactions and 1 billion times more potent than burning fossil fuels. No other process in physics can surpass this efficiency. For now, antimatter propulsion systems, batteries, and warheads remain the stuff of science fiction. Producing and storing antimatter for practical use consumes far more energy than the antimatter itself could release, rendering it unfeasible as a fuel. However, even without imagining futuristic technologies, antimatter is already part of our present, woven into the tapestry of daily life and scientific exploration. In 1940, Canadian chemist Martin Kamen was working at the Berkeley Radiation Laboratory at the University of California. His goal was deceptively straightforward: to create a new isotope of carbon, the elemental backbone of all known life. Together with his colleague Sam Rubin, Kamen irradiated graphite samples, hoping to induce the formation of a previously unknown carbon isotope. For days, they worked tirelessly, with Kamen enduring sleepless nights. One fateful evening, after stepping out for fresh air, Kamen's disheveled appearance caught the attention of a patrolling policeman. Mistaken for an escaped convict involved in a local murder spree, he was detained. Once cleared, Kamen returned to his experiments and finally succeeded. He and Rubin had discovered carbon-14. Though rare in nature, carbon-14 has become a cornerstone of radiocarbon dating, enabling scientists to determine the ages of ancient organic materials. For every trillion carbon atoms in your body, one is carbon-14. Unlike stable isotopes, carbon-14 decays over time, a process that begins when an organism dies. By measuring the remaining carbon-14, scientists can estimate how long it has been since the organism last absorbed this isotope through respiration or consumption. The decay of carbon-14 is a process of balance known as beta decay. During this decay, a neutron transforms into a proton, emitting both an electron and an antineutrino. Similarly, the decay of potassium-40 within your body sometimes produces positrons, the antimatter counterpart of electrons, and neutrinos. This means that all life on Earth, including you, is a natural antimatter factory, generating particles that briefly exist before annihilating with their matter counterparts. The properties of positrons have profound medical applications. In the 1950s, scientists developed a groundbreaking imaging technique, positron emission tomography, PET. By injecting a radioactive tracer into the bloodstream, PET scans track the positrons emitted during decay. These positrons annihilate with electrons, producing pairs of photons with a unique energy signature. Detecting these photons allows for detailed imaging of the body, enabling the diagnosis of medical conditions and mapping of brain activity. PET scans have revolutionized our understanding of how the brain responds to stimuli, from admiring a sunset to listening to a story or gazing at the stars. Antimatter is not confined to our bodies or laboratories, it also exists across the cosmos. Violent astrophysical events, such as supernovae and the collisions of neutron stars, eject antimatter into space. In the 1970s, astronomers detected a cloud of positrons near the Milky Way center. NASA's Compton Gamma Ray Observatory later discovered a fountain of antimatter stretching 3,000 light-years out of our galaxy. The origins of these phenomena remain mysterious, hinting at undiscovered processes in the universe. Despite its presence, the amount of antimatter detected is vastly smaller than the amount of matter in the universe. This imbalance is crucial to our existence. If matter and antimatter had been created in equal quantities during the Big Bang, they would have annihilated one another, leaving behind a cosmos devoid of stars, planets, and life. Yet the observable universe is overwhelmingly composed of matter, with antimatter largely absent. To understand this imbalance, we must journey back to the universe's infancy. In the moments following the Big Bang, matter and antimatter should have existed in perfect symmetry. But something broke this balance. Theorists propose mechanisms such as baryogenesis, where subtle differences in the behavior of matter and antimatter led to a tiny excess of matter. For every billion particles of antimatter, there was one extra particle of matter. This infinitesimal asymmetry allowed matter to survive, forming the galaxies, stars, and planets we see today. The origins of this asymmetry remain one of the greatest mysteries in physics. Experiments at facilities like CERN continue to probe the properties of antimatter, searching for clues to the processes that shaped our universe. As we deepen our understanding, the story of antimatter reminds us of the delicate balances that underpin existence, from the fleeting positrons within our bodies to the vast cosmic structures born from an ancient imbalance. In exploring antimatter, we do more than unravel the universe's mysteries, we confront the profound question of why we are here at all. The dawn of time, a universe born of imbalance. The mystery of why we exist, why matter triumphed over antimatter, is one of the most profound questions in cosmology, a story that begins in the smallest fraction of a second after time itself began. 1/1,000,000th of a second after the Big Bang, the universe was a roiling sea of unimaginable energy, with temperatures reaching 1,000,000,000,000 degrees Celsius. There was no matter, no atoms or particles to provide substance to the cosmos. Instead, there was light, energy, and the nascent forces that would govern reality. At this temperature, following the principle of mass-energy equivalence, the energy began to condense into particles. From this sea of energy emerged quarks and their antimatter counterparts, antiquarks. Each quark came into existence paired with an antiquark twin. Alongside them appeared gluons, the particles responsible for the strong nuclear force. In cooler conditions, these gluons would have the power to bind quarks together into protons and neutrons. But the universe at this stage was far too hot. In this primordial quark-gluon plasma, particles zipped around at incredible speeds, colliding and annihilating one another. When a quark encountered its antiquark counterpart, they annihilated, converting back into energy in the form of photons. This process, repeated countless times, created a near-total annihilation of both matter and antimatter. As the universe expanded and cooled, leptons, such as electrons and their antimatter equivalents, positrons, began to form alongside neutrinos and antineutrinos. However, with the falling temperatures, new quark-antiquark pairs could no longer spontaneously arise from the vacuum. The quarks that remained slowed enough for gluons to begin binding them together, forming hadrons, the composite particles that include protons and neutrons. Similarly, antiquarks formed antihadrons such as antiprotons and antineutrons. As hadrons and antihadrons emerged, they too began annihilating each other. Protons and antiprotons, neutrons and antineutrons collided, converting their mass into energy. By the time the universe was 1 second old, the annihilation was nearly complete. For every billion particles of matter, only one survived. The rest, along with their antimatter counterparts, had vanished, leaving behind a universe dominated by light and radiation. Around 100 seconds after the Big Bang, the universe had cooled sufficiently for nucleosynthesis to begin. Protons and neutrons started combining to form the first atomic nuclei, giving rise to the light elements, primarily hydrogen and helium. But this process would not have been possible without the tiny imbalance that left one particle of matter for every billion particles of antimatter. Without this asymmetry, the universe would have been an endless expanse of photons with no atoms, no stars, and no life. Why did matter triumph over antimatter? According to our understanding of the Big Bang, matter and antimatter should have been created in equal amounts, leading to their mutual annihilation. The fact that matter remains is a fundamental violation of balance in the universe. This asymmetry, though crucial to our existence, defies the symmetry expected by the laws of physics. One hypothesis suggests that there might be regions of the universe where antimatter dominates, forming anti-galaxies and anti-stars. Since the spectrum of light emitted by antimatter atoms is identical to that of their matter counterparts, anti-galaxies would be indistinguishable from ordinary galaxies through telescopes. However, intergalactic winds would inevitably carry regular matter into these regions, leading to annihilation events. Astronomers have yet to observe the distinctive light produced by such annihilations, casting doubt on the existence of large antimatter structures. Smaller antimatter objects, such as clusters of anti-stars, might persist, shedding antimatter particles that blend into cosmic rays. These signals, however, are faint and difficult to distinguish amid the noise of the universe's radiation. Most scientists now agree that the answer lies not in hidden antimatter galaxies but in a deeper asymmetry embedded in the laws of nature. The universe, it seems, may not have the perfect balance or symmetry that we once assumed. Processes such as CP violation, a phenomenon where certain particle interactions slightly favor matter over antimatter, could explain the observed imbalance. Experiments at particle accelerators like CERN continue to investigate these subtle asymmetries, offering glimpses into the mechanisms that shaped our universe. The dawn of time was a battleground, a cosmic war between matter and antimatter. From this struggle emerged a universe dominated by matter, where the tiniest imbalance allowed for the formation of stars, planets, and life. Though the reasons for this asymmetry remain elusive, they are a testament to the delicate interplay of forces and particles that define our reality. As we peer deeper into the origins of the universe, we are reminded of how close existence came to never happening at all. The survival of matter over antimatter is not just a scientific puzzle but a profound reminder of the fragile circumstances that make our existence possible. The answers to this enigma, when they come, will illuminate not only the nature of the cosmos but the very foundation of why we are here. An unbalanced cosmos, the journey to understanding asymmetry. What if the universe as we know it had been perfectly balanced? Would matter and antimatter have annihilated one another in the first moments of existence, leaving behind a cosmos devoid of stars, planets, and life? How did the scales tip so slightly, yet so profoundly, in favor of matter, allowing the universe to take shape? These questions have driven some of the most pivotal discoveries in physics, revealing a cosmos where balance is more elusive than it seems. In 1912, Qian Wu was born in a small fishing town north of Shanghai. Unlike most Chinese girls of her time, she received a formal education, attending a school for young women founded by her father. Her brilliance in academics led her to graduate at the top of her class with a degree in physics from the National Central University in Nanjing. Encouraged by her mentor, Dr. Jing Wei Gu, Wu emigrated to the United States in 1936 to continue her studies, earning her PhD from the University of California, Berkeley, in 1940. In 1944, she joined the Manhattan Project at Columbia University, applying her expertise in beta decay to wartime research. By the mid-1950s, she had become a U.S. citizen and a leading expert in nuclear physics. It was her mastery of beta decay that would lead her to challenge fundamental assumptions about the universe. Charge symmetry. This principle asserts that positive and negative charges are treated identically by the laws of physics. For instance, up quarks, positively charged, and down quarks, negatively charged, should behave identically in mass and in nuclear reactions. Parity symmetry, often associated with handedness, parity symmetry suggests that the universe has no inherent preference for left or right. A mirror reflection of a physical system should behave identically to the original system. Time symmetry. This principle dictates that the laws of physics remain unchanged if the direction of time is reversed, with particles flipping their speed and spin as if the universe were rewound. Together, these principles form the foundation of CPT symmetry. If CPT symmetry holds, the universe should behave identically even under transformations of charge, handedness, and time. But what if one of these principles were subtly broken? In 1956, theoretical physicists Chen-Ning Yang and Tsung-Dao Li proposed that parity symmetry might not hold for the weak nuclear force, a controversial idea at the time. Li approached Wu to discuss the possibility of designing an experiment to test this hypothesis. Wu proposed an ingenious method involving the radioactive isotope cobalt-60. Cobalt-60 decays via beta decay, emitting electrons and gamma rays. Wu's experiment cooled cobalt-60 atoms to extremely low temperatures and constrained them within a magnetic field. If parity symmetry were conserved, the emitted electrons would show no preferred direction, even when the magnetic field was reversed. However, Wu's team observed a clear asymmetry. More electrons were emitted against the magnetic field than along it. Nature, it seemed, could distinguish left from right. This groundbreaking discovery, published in December 1956, shattered the long-held assumption of parity symmetry in the weak nuclear force. The universe, at its most fundamental level, was not symmetric. Despite Wu's pivotal role, the 1957 Nobel Prize in Physics was awarded solely to Yang and Li. Nevertheless, Wu's contributions cemented her legacy as a trailblazer in nuclear physics. Wu's work was only the beginning. In subsequent decades, experiments revealed violations of CP symmetry, the combination of charge and parity, in the behavior of quarks and antiquarks. These discoveries showed that the universe treats matter and antimatter differently, albeit in extremely subtle ways. By the end of the 20th century, CP violation was well established, confirming that the cosmos is slightly unbalanced. Could CP violation explain why matter outnumbered antimatter in the early universe? The asymmetry observed in quarks and antiquarks, while significant, is not sufficient to account for the 1 in a billion excess of matter that remained after the Big Bang. Scientists have since turned their attention to other particles, particularly leptons and neutrinos. Neutrinos are among the most enigmatic particles in the universe. Nearly massless and barely interacting with matter, trillions pass through your body every second without a trace. Unlike other particles, neutrinos exhibit a curious asymmetry. All observed neutrinos are left-handed, while all antineutrinos are right-handed. This raises intriguing possibilities. Right-handed neutrinos. If right-handed neutrinos exist, they may have played a role in the early universe, decaying more often into matter than antimatter. Neutrinos as their own antiparticles. Alternatively, neutrinos might be their own antiparticles, capable of annihilating themselves under certain conditions. This property, if confirmed, could help explain the matter-antimatter imbalance. Current research at particle accelerators and neutrino observatories aims to uncover whether neutrinos violate CP symmetry. Preliminary results are promising but inconclusive. If neutrinos indeed favor matter over antimatter, they could provide the missing piece of the puzzle. Another intriguing hypothesis suggests that pockets of antimatter might still exist, isolated from the rest of the universe. Antimatter clusters, such as antistars, could persist in regions far from regular matter, avoiding annihilation. Instruments aboard the International Space Station, like the Alpha Magnetic Spectrometer, are searching for rare antimatter particles, such as anti-helium-3. By studying the abundance of antimatter in our cosmic neighborhood, scientists hope to extrapolate its presence across the universe. The universe's asymmetry is both its mystery and its salvation. Without the slight imbalance that favored matter over antimatter, the cosmos would be a sea of photons, devoid of stars, planets, and life. The discoveries of Qian-Xiong Wu and others have illuminated the subtle ways in which the universe defies symmetry, offering glimpses into the mechanisms that shaped our existence. As we continue to explore these mysteries, each new discovery brings us closer to understanding why matter prevailed and why we are here. The story of the universe's unbalanced nature is not just a tale of physics, but a profound reflection on the delicate conditions that make life possible.